Is it audible? Yeah, good morning. Okay, fine. So is it audible to everybody? Okay. So I hope you understood what is a continuity equation, right? So this continuity equation, this is the necessary and sufficient condition for a possible liquid motion. Got it? Just a minute, it is glaring. I'll adjust the camera. So for a possible liquid motion, the continuity equation needs to be satisfied. And this was derived based on the principle of law of conservation of mass. Suppose if there is a closed volume like this, then let us say the fluid flow is going out, then this is Q. Then let us say the normal at any instant is this one, and then this is the angle theta. So if the fluid is moving out perpendicular to the surface, then whatever the fluid, if you consider in the opposite direction, fluid entered, this should be equal to per unit time. This should be equal to rate of change of mass within the closed surface. So this is the basic principle that was used to find out the continuity equation. So the liquid mass entered per unit time is equal to rate of change of mass within the closed volume. Within the closed volume. So this is a basic principle that is used. So for an incompressible fluid, so this is del dot Q is equal to 0, where Q is the velocity. Where Q is the velocity. Got it? So do you have any questions on this till this point? for any kind of fluid, whether it is incompressible or not. So this is dou rho by dou t plus q dot del dot rho q equal to 0. So this is general continuity equation. Got it? Any questions till this point? This is the essence of this continuity equation. So here actually the problems that are going to be asked in UPSC is find out whether the liquid motion is possible or not. That is the kind of statement they give. So indirectly what he asked is, he asked us to prove that the continuity equation is satisfied there. So 99% of the cases what he is going to give is the incompressible fluid. So incompressible fluid, that is del dot q is equal to 0, which is nothing but the divergence of any liquid of incompressible in nature is equal to 0. This is the continuity equation. Just a minute. Fine now? So this is the essence of the topic. So there is a possibility of asking the questions in this particular section. That's why actually I have given the summary of all the discussion whatever we had yesterday. Clear? Oh. So you can ask me any doubts if you have. Any doubts? Okay, great. Now we'll solve some problems based on this understanding. So if it is straightforward Cartesian coordinate system, you can straight away apply del dot q and then solve it. But if it is polar coordinate system, then that will be a little bit difficult in nature. So we'll solve some problems on spherical coordinate system and cylindrical coordinate system. So note down one problem. The particles of fluid move symmetrically in space with regard to a fixed center prove that the equation of continuity is dou rho by dou t plus u times of dou rho by dou r plus rho by r square dou by dou r of r square into u. This is equal to 0, where u is the velocity at a distance r. at a distance r. So this is the problem statement he has given. Here, a particle of fluid moves symmetrically in space with regard to a fixed center. So this is indirectly what he asked is the spherical coordinate system. So I hope everybody is aware of what is the spherical coordinate system. I don't need to repeat that. Got it? So here, so this is the fixed point. A particle is moving in space, that is in the radial direction. Now, so if you take a random particle, so this is a kind of random particle, fluid particle we have considered. This is the particle. So here actually I have considered an elemental volume. So this is the elemental volume. So this length is dr because this is the length along the direction of the radius dr, and then this angle is theta. So this angle is theta. Then obviously what is this length? So till this point the radius is r, then this will be r d theta. This is d theta, sorry, at an angle of theta. So d theta at an angle of theta. So r d theta is this length, and then the elemental volume, right? So that is inside there will be a volume particle. So that means this is a three-dimensional. Just try to imagine that this is three-dimensional. Like this. I hope you are able to make out the diagram. An elemental volume I have drawn. Understood or not? You want me to repeat the diagram? See this. This is in spherical coordinate system. So I have identified an elemental volume in spherical coordinate system. So the elemental volume so constructed in case of spherical coordinate system will be, there has to be a length along the radial direction, there has to be a length along the theta direction, and there has to be a length along the phi direction as well. Got it or not? Right? So along the theta direction, so because the angle is d theta, then this is r into d theta, and along the radial direction the length is dr. So we are talking about only the lengths, right? So the angle, if it is given, that needs to be converted in terms of the length. So the relation between length and the angle is the multiplication with respect to r, right? So because in any circle you can think of, so on this circle if the radius is r, then this particular elemental length, that is the perimeter. So if you call this as dl, then this dl will be equal to r into d theta. So this is in case of circle, right? So here actually in spherical coordinate system, so we can imagine a circle along the theta direction, and we can imagine a circle along the phi direction as well, right? So this is r d theta, then this length or the vertical length will be obviously r sin theta into d phi. R sin theta into d phi. So one is d theta, another is d phi. So in the d phi direction, the length will be r sin theta into d phi. I hope you understood that. So putting that three-dimensional thing on the blackboard is very tough. So try to imagine an elemental volume. Just imagine a shape of ball, and then on top of that there is one more ball. Imagine that way. So there are two different balls, one inside the other. Then try to cut one piece of the ball. So that piece of the ball is the shape of the elemental volume. Got it or not? So inside there is a ball and outside there is a ball. Try to cut one piece from both the balls together. So that shape, if you identify it, then this is the kind of shape you are going to get it. Got it or not? Understood? I hope everybody understood. Okay. So this is the elemental volume. Now the velocity along the radial direction, what he has given is, this is u is the velocity of the fluid. So if u is the velocity of the fluid, then the fluid that is getting entered into the fluid, so get entered into the space, will be opposite to this particular direction, that is minus. I have explained this concept yesterday. The convention is taking away from the point. So that is the velocity direction. But what we want is, we need to calculate the volume of the fluid that is entering the surface. So that's why we take the opposite of it. Understood? This I have discussed yesterday. As the fluid, so directional convention is outside, but the fluid that is needed is coming inside. That is why it is opposite. Got it? So the volume of the fluid entered. In radial direction. So this is only the radial direction, because he said that there is no flow along the theta direction. That means the flow is only away from the central point. So away from the fixed point, we mean that is only the radial direction. There is no flow of the fluid along this surface or along the bottom surface. There is only one that is going out. Got it or not? So this length is dr, and this is r d theta, and this is r d phi. So r sin theta into d phi. I hope you understood why it is r sin theta. Got it? So this is all related to coordinate system. Nothing related to fluid dynamics here. So this is completely related to coordinate system. Everything you should be able to understand. Everything. So in the radial direction, so the volume of the fluid that is entered in the radial direction is equal to minus of, so here the mass of the fluid, let us say dm. Dm is nothing but, so density into the elemental volume. So mass of the fluid, dm is equal to, so that is entering, that is minus of dr into dou by dou r of u into volume of this. So volume is rho into dr into r d theta into r sin theta d phi. Here the mass of the fluid, so dou m by dou r. So this is minus dr into rate of change of mass. This is, that means if the fluid is moving in this direction, so the rate of change of mass along this particular direction getting multiplied by this length dr is nothing but the volume of the fluid that is effectively entered into this elemental volume. Correct or not? Understood or not? I need response. Okay. So camera, I think so there is a little bit of glaring there because of the outside light. See this, the volume, right? So suppose, let us say, rather than that shape, you try to imagine a box like this. So in Cartesian coordinates, you will be able to make out immediately. let us say this is the box. Now there is a fluid that is entering into this, and then the mass of the fluid within this particular volume is m, let us say. Then this length is dr, and this length is this horizontal length r d theta, and this vertical length r sin theta d phi, let us say. So these are the lengths. If this is the length, then if the fluid is entering with a velocity of u, and let the mass of the fluid is rho, then density of the fluid is rho, and the velocity of travel is u, then whatever the mass that is accumulated here, right? So this is going to be changed because there is a movement of the fluid here because of this velocity, right? So there is a movement of the flow. Then the rate of accumulation here, so that is nothing but the change over the length of dr, because this is the direction of u, there is no other direction. So there is no flow vertically, there is no flow bottom, and there is no flow side this way or the other way. Now there is only one directional flow that is going this way. So this one directional flow, whatever is going, right? So it causes some mass of the fluid to change, correct or not, over the length of dr. So that can be counted by taking the derivative of this mass with respect to r and getting multiplied by this dr, that is rate of change of mass with respect to the radius multiplied by entire length. That is the total change over the complete volume, correct or not? So this is exactly what we have done except for the shape. So this is dou by dou r of mass of the fluid within. So mass of the fluid, you can get it because there is a velocity u into rho into dr into r d theta into r sin theta d phi. So this is nothing but dr d theta r d theta into r sin theta d phi is nothing but the volume part, and this is rho, and this is u is the velocity, rho is the density. So this is density and this is the velocity. Sorry, this is dm by dt. Yeah, got it? So the mass of the fluid that is getting accumulated within this elemental volume is given by minus dr into dou by dou r of u into rho into dr into r d theta into r sin theta d phi. So this is the way we have calculated is by considering the fluid is entering, but convention going out. So that's why this is the accumulated fluid. Now the same thing should be equal as per the continuity equation to the rate of change of mass, that is time rate of change of mass is equal to space rate of change of mass. So that is the continuity equation. Got it? So over a second, if there is a certain fluid accumulated here, the same fluid that might have come from all the surfaces, that is the continuity equation. So whatever the fluid that is coming within from all the surfaces is this one. So this is per unit time. Now same thing, it should be equal to the rate of change of mass of this one. So that is the mass will be rho into dr into d theta, sorry, dr into r d theta into r sin theta d phi. So this is the mass. Now the rate of change of mass, that is d by dt of mass. This should be exactly equal to this quantity because this is the mass of the fluid that is entering all the surfaces. This is the change of the mass with respect to the volume where these surfaces are enclosing. Clear? Any questions on this? Change of mass. So forget about all this discussion. I will give you a common sense wherein suppose there is a box. On this particular box, let us say this box is kept on a flowing water. Then, so this fluid is continuously moving within, so it is flowing into the box and coming out of with all the surfaces. Now by common sense we can make out whatever the fluid that is entered into the box with all the surfaces together, right? it should be exactly equal to the rate of change of mass of the fluid within the box, correct or not? So it started with open box, that is there is nothing inside. Now fluid started entering. So fluid started entering in all the directions. So immediately when you keep the box within the flow, then fluid tried to enter in all the directions together into the box. Now whatever the mass of the fluid that is entered, this should be exactly equal to the mass that entered from all the surfaces, right? In 1 second, if you count it, whatever the fluid after 1 second that got placed within this particular box, if I count it, then that count should be exactly equal to the fluid that is entered over all the surfaces together. Is that understood, Samrin? So this is the same concept what we are using here. Per unit time, we are counting it. So per unit time, now the shape of the box is different, except for that there is no other thing is involved here. The shape of the box, just imagine the shape of the box is one length is dr, another length is r d theta, another length is r sin theta d phi. These lengths we got it because we are trying to use the spherical coordinate system. In the spherical coordinate system, or whatever may be the coordinate system you can think of, if you want to consider an elemental volume, you have to identify 3 different lengths. So, but in spherical coordinate system, there will be only one length and 2 different angles are there. The angles can be converted into the length or the perimeter enclosed by certain angle. So that angle, for angle theta, the angle is d theta. Obviously, the length enclosed on the periphery is equal to r into d theta. And suppose the vertical angle in the xy plane, if it is equal to phi, so that is elemental angle is d phi and d phi, but the length is projected, the vertical component will be r cos theta and the component of the xy plane will be r sin theta. This r sin theta is making an angle of d phi on the xy plane. That d phi value, if you getting multiply r sin theta into d phi, is nothing but the length along the phi direction. Got it? So those lengths actually, for a so simplicity, I have given it here as if like it is a box, but the box shape is different. Got it? So because you are trying to cut from the ball, yeah. So now the fluid that is entering from all the surfaces, right, should be equal to rate of change of accumulation or rate of accumulation of the mass within this particular box. The fluid that is getting entered in all the directions is nothing but, so that is d minus dr into dou by dou r of, so rho into u into r d theta into r sin theta into d phi. Got it? So sorry, this is not dr. So u into rho into r d theta into r sin theta into d phi. So this is the area getting multiplied by velocity is nothing but the rate of transfer of fluid across that particular cross-sectional area. That cross-sectional area is r d theta, r sin theta d phi. This is the area that is perpendicular to the radius direction. So that is getting multiplied with the velocity vector u, and rho, if you multiply it, this will become the mass. Clear? So this rate of change of mass with respect to the radius getting multiplied by dr is nothing but the total mass that entered over the surface which is perpendicular to the radius into the closed volume specified by this box. Is this understood? Okay. Now this is one part of the continuity equation. The other part will be, you will be approaching what is the rate of change of mass within this particular volume. So rate of change of mass. For that, the mass is nothing but rho into dr into r d theta into r sin theta d phi. So here this part is dv. Simply dv in case of spherical coordinate system, it is always like this only, because dr is a length, r d theta is a length, r sin theta d phi is a length. So all the 3 lengths getting multiplied will be enclosing a elemental volume given by dv. So this part is dv. So this dv, once you identify it, multiply with the density will give the mass of it. Now the time rate of change of mass should be, so this is time rate of change of mass, should be equal to the right side part of it. So the right side part of it is minus dr into dou by dou r of u into rho into r square sin theta into d theta d phi. Got it? R square sin theta d phi. So if there is a change in the rho value, let us say rho is a function of time, then rest of the things are only the space coordinates. Then dou rho by dou t into dr r square into dr into r square sin theta dr into d theta into d phi, and this value so is equal to minus dr. Can you note down this? I am going to erase it and rewrite it. Let me know once you note it down. So this I have not written, so I will rewrite this. Note down till this point. Done? Okay. Now from this, right, so from this step, here this is with respect to time. So dr into r square sin theta into dr into d theta into d phi into dou rho by dou t. So though d by dt is for complete, so rho is the only possible time domain function. So that's why dou rho by dou t and rest of the things are the space coordinates. You can keep it outside. And this is, if you bring this minus to the other side, then dr into dou by dou r of, so this is dou by dou r of u into rho into r square, and this is the only possible, the function that is related to r. Then the rest of the things are sin theta into d theta into d phi equal to 0. This is the continuity equation. Now this continuity equation, if you further simplify it, then this will be r square into dou rho by dou t into sin theta into dr d theta d phi plus dou by dou r into u into rho into r square into sin theta into dr d theta d phi. This is equal to 0. Now this part you can take it common as a factor and then take it to the other side, it will become 0. Then this will be r square into dou rho by dou t plus dou by dou r into u rho r square is equal to 0. Got it? So if you take this as a separate function, because actually r square into u, r square into u and rho separate, then this will be r square into dou rho by dou t plus, so apply uv formula on this. Yeah, you can keep it as it is. Dou rho by dou t plus 1 by r square into dou by dou r of u into rho into r square. So this is the continuity equation. Got it? Understood? So if you apply uv, you are going to get this step. That's it. So this part is as it is, and u into dou rho by dou r. So here u into r square divided by r square, that is r square will cancel and u will be left over, and dou rho by dou t plus 1 by r square into rho, you can take it outside, r square into u. So that is dou rho by dou t plus u times of dou rho by dou r plus rho by r square into dou by dou r into r square u. So this is equal to 0, is nothing but the continuity equation. Understood? Understood or not? Is the concept clear? Okay. So this is how actually there is a possibility of asking the questions for different kinds of coordinate system. Here the difficulty is understanding the coordinate system rather than understanding the continuity equation. So appropriately you need to model that coordinate system and then try to express based on the variables whatever he give it. Now this is the case of spherical coordinate system. Now if you understand this, I'll just give a brief view on the cylindrical coordinate system and then I will give one problem as homework. You try to solve that. Note down the problem. A mass of fluid is in motion. A mass of fluid is in motion so that the lines of motion lie on the surface of coaxial cylinders. The surface of coaxial cylinders. Show that the equation of continuity is dou rho by dou t plus 1 by r dou by dou theta rho into qr plus dou by dou z rho into qz is equal to 0. This is the problem statement where q or qz are the velocities qz are the velocities perpendicular and parallel to z. First, try to understand this problem statement and what he asked for. Can you tell me what he asked for? Understood problem statement? No. Anybody else? See this, a mass of fluid is in motion so that the lines of motion lie on the surface of coaxial cylinders. Coaxial cylinders we mean there is a cylinder here and then there is one more cylinder that is enclosed in this. So this is the cross sectional view of a coaxial cylinder. So this is one cylinder, on top of that there is one more cylinder. Now the lines of motion are, so just imagine this way, there is a cylinder and within that there is one more cylinder. Let us say the inside cylinder is trying to rotate on its own, it's about its own axis. Then inside cylinder is rotating, then the water inside that is enclosed between the two cylinders also will exactly go in a circular manner like this. Correct or not? Right? So here in this particular case what he is saying is there is a flow along the theta direction and there is a flow along the z direction as well. So that's why what he said was, so where QR and QZ are the velocities perpendicular and parallel to the Z, perpendicular and parallel to the Z. So let us say this is Z axis. Then so on the XY plane, so this is Z axis, on the XY plane in polar coordinate system or the cylindrical coordinate system there will be a radius like this and this radius will make an angle of theta. So this is on the XY plane, not XZ. Got it? There is an angle of theta. So the direction of flow, so this is QZ direction and then the flow along the radial direction, this is the direction of R. So this is the QR direction. So on the coaxial cylinders the water is flowing away like this and the water is flowing so in the vertical direction, so not in the circular direction. Got it? Understood? Now based on this understanding, so you have to identify an elemental volume here. So this elemental volume, so that will be like this. So this is the shape of the elemental volume. Suppose if I cut one piece here, so I just cut one piece here and took it out. This is the kind of shape you are going to get it, right? So this is circular in nature and this is circular in nature. and this is circular in nature, and this is also circular, but this is straight line, and this is straight line, and this is straight line. This is also straight line. This is a straight line. So this is the kind of shape, elemental volume, correct? Lizu, so I am just repeating. See this, there is a flow along the z direction. There is a flow along the r direction. So this r is on the xy plane, right? So these are coaxial cylinders. Within this there is the volume that is getting accumulated. Now the cylinders may be too far away, right? So there is one cylinder and there is one big cylinder. Now within that there is a fluid. The fluid flow that is happening is one vertically upward, one is radial. So both the directions together the fluid is getting filled there. So for that, if you want to consider an elemental volume, this is the kind of shape you are going to get it for an elemental volume. So this length, the horizontal length will be obviously dr and the vertical length will be dz. And as this is making an angle of theta, so this is angle theta, d theta. So this is angle d theta. Obviously, this length will be r into d theta. So all the three lengths you have got. Understood? All the three lengths you have got. Now if you want the elemental volume, the product of all the three. If you want to identify the mass within the fluid, within the elemental volume, that is rho getting multiplied by the volume. So you have to take the time rate of change of rho getting multiplied by this elemental volume. That is one side of the continuity equation. On the other side of the continuity equation, as there is a flow along the z direction and along the r direction, along the z direction, we mean this is the direction of the flow. If this is the direction of the flow, so this direction of velocity is qz, and this is the area of cross section, which is the top area of cross section. So this, if you want to identify the elemental volume, this length dr getting multiplied by r d theta is this length. This is the area. So with that area, with a velocity of qz, the water is flowing out. Correct or not? The water is flowing out across the surface, dr into r d theta. Got it? And there is one radial component of velocity that is coming in this direction. This is qr, and this qr is coming perpendicular to the surface of r d theta into dz. So the area getting multiplied by the velocity is nothing but the rate of flow of mass. So you need to multiply with rho. So that is, if you wanted to identify the mass of the fluid that is crossing one particular surface, you can identify that is rate of change, that is r d theta into dz is the cross sectional area, and then you need to multiply this dr, right? So dr getting multiplied by the area of cross section, you need to identify, and rho into the velocity in this direction. For that, you need to take the derivative with respect to r. So the water crossing, suppose if I name the surface as, so this is A or P, Q, R, S, and this correspondingly P dash, Q dash, R dash, S dash. Now the volume of the fluid that is crossing QR, R dash, Q dash. The volume of the fluid that is crossing Q dash R dash R is equal to, or crossing or entering the surface. So entering, you will be taking minus sign, and then dr getting multiplied by rate of change with respect to r, dou by dou r of velocity into area of cross section. Velocity is qr and the area of cross section of this is r d theta into dz multiplied by the density. So this is the volume of the fluid that is crossing this surface r dash q dash q. Is this understood? Understood or not? Other than Avinash, yeah. So I hope everybody got a fair idea on this. Then there is a flow along the z direction also. Then the rate, so the flow of water that is going inside along the surface or across the surface, this particular surface is given by so this is not mass, so this is not volume, this is mass. The mass of the fluid, because you are multiplying with rho. Yeah. Mass of the fluid crossing the surface PQRS. So here, this is the way it is coming, right? Then the area of cross section will be PQRS. So the area of cross section dr into r d theta. Minus of dou by rho into qz into, so this is the area of cross section, this is the area of, so this length is dr, this is r d theta, dr into r d theta. And then the way it is moving is with respect to dz, dou by dou z. And the length getting multiplied is dz. So this is the mass of the fluid. Got it? Understood or not? So this is correct, but actually, so what is this velocity? A mass of fluid is in motion so that the lines of motion lie on the surface of coaxial cylinder, so that the equation of continuity is where QR and QZ are the velocities perpendicular to perpendicular and parallel to Z. Yeah. Yeah, so this is as per our understanding, this procedure is correct only, but actually in the problem statement what he said was the direction of flow is not QR, Q theta he has given. Maybe that is the difference. Yeah. Okay. Anyway, so we will solve for this particular case only. If the fluid is moving along QR and QZ, then this procedure is 100% correct. Yeah. So this is the total fluid that is entering along the QR direction and along QZ direction. Now, this mass of the fluid that is coming in both the directions together should be exactly equal to the rate of change of mass that is enclosed within this particular volume. Correct? Now, the mass of the fluid will be rho into, so dr into r d theta into dz. So this is the mass of the fluid. So this is dm. Now, if you want to take the derivative with respect to time, so this will be dou by dou t of this entire mass. So this dou by dou t of this entire mass is exactly equal to sum of this equation number 1 and equation number 2. So this is equation number 2. So these two equations you need to sum it up and then simplify the equation. You are going to get it. Got it? Understood? Or do you have any questions on this? So here the procedure is simple and straightforward, whatever we learned in vector calculus. So that is nothing but the divergence theorem. You are applying divergence theorem here, nothing more than that. Divergence theorem, what it says, double integral over the surfaces f dot ds is equal to triple integral over the volume f del dot f dv. So this is the divergence theorem. This divergence theorem, physically what it states is, whatever the fluid that is entering from all the surfaces of any closed surface, that is, imagine a room. So room will have 6 different surfaces. From all the 6 surfaces, if there is a flow that is happening, so that flow of water that is crossing all the surfaces together should be equal to the volume that got changed within this particular room. So that is as simple as that. Same thing we are trying to prove it here. So here, first you need to identify the direction of the flow. If QR is given and Q theta is given and QZ is given, that means the flow is happening in all the 3 different directions. Suppose if only 2 are given, the flow is happening in only 2 directions. In this particular case, what he has given is the flow is along QR and the flow is along QZ. So there is a Z direction flow and there is a R direction flow. Then the flow of mass that is crossing this surface and the flow of mass that is crossing this surface, both we are counting it. And then as the convention is opposite, so that you have to consider with the negative sign. So the mass that is crossing both the surfaces together should be equal to the mass of the fluid that is changed within this particular volume. So that is this part. So the sum of these two should be equal to this one. That is nothing but the continuity equation. Clear? Got it? Yeah. So here actually in this problem statement in textbook what he is solved is not for QR. So he considered for Q theta. That is the difference. So if it is Q theta, then the mass of the fluid that is crossing this particular surface, that is, yeah, PQ and then Q dash and R. Yeah. So the mass of the fluid that is crossing PQ, Q dash and P dash. So this surface actually you need to consider it. Now if this is the case, yeah, so that surface you need to consider and then you need to identify the mass of the fluid that is crossing the surface, and then if all the 3 directional flow is happening, then that also you need to add it for this one and this one together. You need to add the fluid motion that is causing base of the other surface, and all the 3 together should be equal to the rate of change of mass. That's it. Clear? No, not in this case. I am giving in general, overall, for the complete problem statement. Suppose if there is a complex flow that is happening in all the 3 different directions, you need to consider all the 3 different directional mass. Yeah, that's it. Got it? So 3 directions. So as the flow is happening from here in this direction, this is one mass of fluid, and the flow, if it is happening in this direction, this is another mass of the fluid that is crossing this surface. And if there is a mass of fluid that is crossing this way, this surface, that also you need to consider if it is happening. So that is the complex level of continuity equation. Yeah, like in previous case. Yeah. No, in previous case, there is only one directional flow, that is a space flow, where there is a flow that is happening only in the radial direction. But this is happening in 2 different directions, R direction and Z direction. But the next level of complexity will be R, theta, Z, all the 3 directions. If there is a velocity, then you need to consider 3 different components here. And left is always 1, because this is the rate of change of mass within the closed volume. Clear? Okay. So, do you have any questions on this? So you try to finish this and then try to prove this one. Yeah. If you don't get it, I am going to solve it for you. Clear? Okay, yeah. So that's all for today. So in the next class, I am going to take up the boundary conditions and vorticity vector. So with that, all the fundamental aspects of the fluid flow is complete. Only the advanced parts will be there. Yeah. So vorticity vector and the boundary conditions. Those are also straightforward, simple only. Yeah. So thank you. Good morning. Bye bye.